Something is tearing the universe apart. It's not just growing, it's accelerating. The expansion is speeding up, driven by a force that makes up more than 2/3 of everything. And it's completely invisible. That's the mystery. Dark energy, the biggest unsolved riddle in science. A cosmic ghost pushing galaxies away from each other. Faster every day, we're going to look at 30 different proposals for it. 30 distinct, mind-bending ideas. Some revive Einstein's greatest blunder. Others say our universe is just a membrane floating in higher dimensions. We'll consider if it's a dynamic field, or an illusion from lumpy space, or maybe a sign that gravity itself is wrong. Wrong on the largest scales. What single idea could solve a mystery that profound? 1998, that was the year. Two teams of scientists, one led by Saul Perlmutter, the other by Brian Schmidt and Adam Rees. They were looking at supernova, exploding stars, using them as mile markers to measure the expansion of the universe. How fast it was growing over huge distances, and everyone thought it would be slowing down. That was the expectation, all the gravity from all the galaxies. It should have been pulling inward, putting a brake on everything, on that initial push from the Big Bang, but the data was different, the distant supernova. They were too faint, which meant they were farther away than they should have been, farther than the slowing model predicted, so the only explanation. The expansion wasn't slowing, it was speeding up. Something was pushing the galaxies apart. They called it dark energy, but that name, it was just a placeholder. For what we don't know, the teams were shocked. They spent years checking, rechecking, certain they had made a mistake, but they hadn't. The evidence was solid. Then later, measurements came in from the cosmic microwave background, the afterglow of the Big Bang, and it confirmed the picture independently. It showed the geometry of the universe. A geometry that only works if this repulsive energy, this dark energy, makes up about 68% of everything, so our understanding of cosmic destiny. It was rewritten just like that. The universe isn't heading for a collapse or a steady coast. It's flying apart, driven by a force we can't see it. We can't touch it, we can't detect it directly. It's the ultimate puzzle, written into reality itself. So what's causing it to even start looking? You have to question everything. The most basic assumptions. To explain why the universe is expanding faster, you have to look at the equations for the cosmos. Albert Einstein published his theory of general relativity in 1915. And then he had a problem. His own equations showed a dynamic universe, one that should be expanding or contracting because of gravity. But at the time, everyone thought the universe was eternal and static. Einstein believed that too, so he did something. He added a fudge factor. He called it the cosmological constant. It's symbolized by the Greek letter lambda. This term was a repulsive force. It would balance gravity's pull on the largest scales. That would create the static cosmos people thought they saw. It was a constant energy density, a property of empty space itself. Then, years later, Edwin Hubble proved the universe was expanding. Einstein called the cosmological constant his greatest blunder. He took it out of his equations. He thought it was unnecessary, but that wasn't the end. In 1998, dark energy was discovered, and Einstein's old idea came back. The simplest explanation that fits the data is that dark energy is the cosmological constant. It's a constant, unchanging energy in the vacuum. Empty space isn't really empty. Think of it as a quantum foam. Virtual particles wink in and out of existence. That quantum activity gives the vacuum a baseline energy. This energy creates a negative pressure. It's like a cosmic anti-gravity pushing space itself apart. There's a profound elegance to it. The universe has a built-in repulsive factor. It's a feature, not a bug, but this elegant solution has a huge puzzle. It's called the fine-tuning problem. When physicists calculate the expected energy of the quantum vacuum from first principles, the number is catastrophically wrong. It's off by a factor of 1 with 120 zeros after it. That's not a small error. It's the largest discrepancy between theory and observation in all of science. For the cosmological constant to match the gentle acceleration we see, its value has to be incredibly tiny, but not zero. Why is it so perfectly balanced to allow galaxies and stars and us to exist? This fine-tuning feels like a cosmic coincidence of unimaginable precision. So the cosmological constant is still the standard model. But these deep philosophical puzzles make us ask, is dark energy really this simple, static constant? Or is it something else, something that changes and evolves, which leads to the next idea? But the constant might not be constant. That's the second idea. The cosmological constant is just a number set from the beginning, but nature usually moves, so maybe dark energy is dynamic, something that changes, that has a history. That idea is called quintessence. It's not a property of empty space. It's a field filling everything. Like the Higgs field gives particles mass, a new kind of energy field, a fifth element. That's where the name comes from, that ancient idea of ether. And this field isn't uniform. It can change. Its energy density can slowly drop over cosmic time. Or in some models, it can even interact very weakly with matter. That dynamism is the appeal. It could solve the coincidence problem. Why is dark energy's density roughly the same as matter's density right now in our era? If dark energy were a true constant, that's a staggering coincidence. A brief moment in 14 billion years where the two are comparable. But if it's a field that evolves, it could naturally track matter's density. Only rising to dominance recently, as Paul Steinhardt has argued, that makes now less of a bizarre accident, more of a natural outcome. There are many versions of quintessence. Some are tracker fields designed to follow matter's density for most of history, then break free. Others have exotic equations of state, strange relationships between pressure and density that, in theory, could be measured. Then the question, is quintessence a new, fifth fundamental force, one so subtle its effects only show across the vast emptiness between galaxy clusters? It's a compelling story, a universe alive with changing fields, where the acceleration we see is just one chapter. But if a field can change, could it also clump? Could dark energy have structure, invisible hills and valleys in space itself? That thought pulls us toward something even stranger. Maybe we've been asking the wrong question. The third idea gets rid of dark energy completely. It says maybe we don't understand gravity. General relativity, Einstein's theory, might not work over the huge distances between galaxy clusters. That's the idea of modified gravity. You're not adding a new force, you're rewriting the one we already have. The simplest version starts with something called F of R gravity. The R is for the Ricci scalar. That's a math term for the curvature of spacetime. In Einstein's equations, gravity is proportional to that curvature. It's a simple, straight line, but F of R theories ask, what if that's not right? What if, on cosmic scales, the curvature responds differently? Think of a spring. Pull it a little and it pulls back with a familiar force. That's general relativity in the solar system. It works, but if you could stretch that spring across a continent, the metal itself might change. It could get softer. It could lose its tension over those huge distances. In F of R gravity, you modify the math of spacetime itself. You tweak the equations so gravity weakens over the largest distances. That weakening looks like an accelerating expansion. From here, it would seem like a force is pushing galaxies apart. But there's no dark energy. It's just gravity, acting in a new way on scales we've only just started to measure. People like Alexei Starobinsky showed how these math adjustments could, in theory, reproduce the acceleration we see. The appeal is deep. it solves the fine-tuning problem. You don't need that strangely small cosmological constant. The universe is simpler, no mysterious substance making up most of it, but this rewrite has huge problems. Any new gravity theory has to pass the tests the old one passes perfectly. It has to explain Mercury's orbit. It has to account for starlight bending around the sun. It has to match the timing of signals from orbiting pulsars. For F of R theories to work, they have to turn back into ordinary general relativity in places like our solar system. They have to hide their modified nature everywhere we've already looked. Building a theory that does both explains cosmic acceleration and passes local tests is like making a key that only works in locks we haven't tried. It's a tightrope walk, so the choice is fundamental. Is the universe mostly made of something we can't see, or have we misunderstood the force that shapes everything? Questioning gravity, that cornerstone, opens the door to even stranger possibilities. The two biggest mysteries might actually be one thing. Dark matter holds galaxies together. Dark energy pushes them apart. They seem like opposites, but there's this fourth idea: maybe they're just different phases of a single substance. That's the Chaplygin gas. Named for a Russian physicist, Sergei Chaplygin, it's this perfect, exotic fluid that fills everything, and it follows a bizarre rule. Its pressure is inversely proportional to its density. You squeeze it and it pushes back less. That's the opposite of how most things work. It's like an anti-spring. In the early universe, when everything was dense, this fluid's energy density was high. Under that rule, it would behave exactly like cold, dark matter. It would clump under gravity. It would form the scaffolding for galaxies. It would be the unseen glue. But then the universe expands, the density of this fluid drops, and the strange rule flips its nature. When the density gets low enough, the pressure turns negative. Deeply negative, and in cosmology, a negative pressure creates repulsion. So the substance that once glued everything together now starts pushing it apart. The glue becomes a propellant. It unifies the dark sector in one sweep. Two puzzles, one solution. A single thing that evolves from a clumping matter into a smooth, accelerating energy. The roots of this idea go into string theory, into Brane cosmology. In some models where our universe is a membrane floating in higher dimensions, the Chaplygin gas just emerges. As a candidate for what fills our brain, it's not just convenient, it's a mathematical possibility from our most ambitious theories. But then elegance faces data. The model runs into tension with observations. With the large-scale structure, the cosmic web we see, for it to act as dark matter early on, it has to clump in a very specific way. The observations suggest it might not clump quite enough to seed the structures we actually find. It's a beautiful, unifying story that might be just a little too perfect for the messy universe we live in. Still, the core question lingers. Could the dark side of the cosmos be simpler than we think? Not two separate unknowns, but two expressions of one underlying reality. This drive to unify pushes our thinking. It suggests the answers might be written in dimensions we cannot see. Our reality might be a surface, a sheet. A membrane floating in a larger space. That's the idea from string theory. We have 3 dimensions of space, one of time, but that could just be our local experience. There could be more dimensions curled up or stretched out where we can't go. In brain-world cosmology, our whole cosmos is one of these membranes. It sits inside a higher dimensional realm. The bulk, all the particles we know, the forces light, matter, the nuclear forces, they're stuck to our brain. They can't leave, but gravity is different. Gravity, the curvature of space-time, might be able to leak. It could seep off our brain into those extra dimensions, and that changes everything about gravity on the largest scales. Think of a shadow on a wall. The shadow moves, changes shape. You might think the object itself is moving in a strange way. but the real cause is a hidden light source shifting in a room you can't see. In the same way, what looks like a mysterious repulsive force on our brain dark energy could just be the shadow of gravity behaving differently in the higher dimensional bulk. There's a famous model named for the physicists Gia D. Valle, Gregory Gabadadze, and Massimo Perotti, the DGP model. It proposes a specific way gravity leaks. On small scales, like inside our solar system, gravity is strong, bound to our brain. It behaves exactly as Einstein predicted. But over cosmic distances, gravity's grip weakens. It dissipates into the extra dimensions, and that weakening from our perspective on the brain looks exactly like an accelerating expansion. There's no dark energy fluid. There's just gravity diluted by the vastness of the bulk. Theorists like D. Valle have worked on testable predictions. These ideas leave subtle fingerprints. The way galaxies cluster, how gravitational lenses bend light over different distances, these might show a deviation from the standard predictions. We could, in principle, measure the ghostly influence of the bulk. The implications are staggering. It means every galaxy, every star, every one of us exists on a kind of cosmic island, a slice of a reality that's far grander and more hidden than we ever suspected. The acceleration of the universe becomes a clue that we are not alone in the higher dimensional dark. But then what if the secret isn't in other dimensions, but woven into the fabric of our own? Space could have frozen, not into ice, but into something else, a new state. That's vacuum metamorphosis. Think of water. At 100 degrees, it boils. It goes from liquid to gas. The substance is the same, but its properties change instantly. Now take that idea and apply it to the whole cosmos. The universe expands and it cools. Everything cools, the matter and the fabric of space-time itself. So this model says there's a critical temperature, and when the expansion cooled the vacuum to that point, everything shifted. The quantum vacuum, that background of activity, it went through a phase transition. Its energy density changed abruptly, and that change launched the acceleration we see. It wasn't gradual, it was a gear shift, like a car on a highway cruising, and it switches from a gasoline engine to an electric motor seamlessly. The ride continues, but the source of propulsion is new. The driver wouldn't feel it, you'd just see the result, the car maintaining speed. In the universe, the result is that push, dark energy. What's beautiful is the connection to something almost tangible. The trigger for this change is tied to a specific mass scale in physics. Some versions link it to the neutrino. That ghostly particle barely interacts with anything. It's like the universe was waiting, cooling and expanding until it hit a threshold defined by these tiny, fundamental weights. Then, click. A new era begins. Physicists Robert Caldwell, they explored this to sidestep the fine-tuning problem. Instead of a cosmological constant set perfectly from the start, the acceleration emerges. It's a consequence, the universe reaching a milestone in its cooling. And this model isn't just a story, it makes predictions. A phase transition in the vacuum would leave an imprint on how cosmic structures grow. Galaxies and clusters would form in a subtly different pattern. Future telescopes mapping in detail could look for that signature, so the question is profound. Could the universe today be the product of a cosmic winter, a moment when the vacuum itself crystallized into a new form, setting the fate of everything in motion? This idea blurs the line, the largest scales and the smallest. It suggests the quantum realm holds the key to our expansive destiny. The universe could be a projection. A hologram, that's the seventh idea, holographic dark energy. It comes from black hole physics. There's a principle there, the information about everything inside a black hole. It's not stored in the volume. It's on the surface, on the event horizon. Every atom, every star that falls in, its information gets painted there, on that two-dimensional boundary. It's like a DVD. The disc is flat, but it holds the data for a full three-dimensional movie. Our universe might work that way. The three-dimensional space we see with all the galaxies could be a projection. From information stored on a distant surface, the cosmic horizon, this is a serious proposal. From quantum gravity and information theory, physicists like Yi-Fu Kai have applied it to dark energy. Here's the leap. If the universe is holographic, there's a fundamental limit to how much information, how much entropy can exist inside any volume. That limit is set by the area of the boundary. Not the volume, the area. So as the universe expands, its horizon grows. The farthest distance we can see, the area of that horizon increases, and the maximum possible information content of the cosmos grows with it. Holographic dark energy proposes that the energy density of the vacuum, the thing causing acceleration, is tied to this information limit. It's determined by the size of the cosmic horizon. A simple analogy, a digital screen. The number of pixels on that screen limits the detail of the image. You can't have more detail than there are pixels. The universe might be like that. Its fundamental pixel count is set by the area of its horizon, and the energy of the vacuum, dark energy, comes from filling those pixels with information. As the horizon grows, the number of pixels increases. The energy density evolves in a specific way. It can naturally lead to acceleration, and it might solve the cosmological constant problem. That huge fine-tuning issue just vanishes because the energy density isn't a random number set at the beginning. It's dynamic. It's determined by the size of the universe itself. A self-regulating mechanism. This idea is profound. It doesn't just add a new substance, it changes what reality is. It says the universe is fundamentally informational. The acceleration we measure isn't from a mysterious fluid. It's a consequence of the cosmos hitting its data storage limits, a cosmic pixelation effect. Playing out on the grandest scale, it bridges quantum bits with the fate of galaxies. If this is true, then every measurement we make is reading a cosmic code. Written on the boundary of everything, space-time might be woven from threads, tiny loops. That's loop quantum cosmology, the smooth fabric of relativity. It's an illusion. A large-scale mirage. Reality at the deepest level is granular, quantized loops of gravity. They weave together into the geometry we experience. It's a tapestry, not a sheet. Apply this quantum geometry to the whole universe, and you get something else. A universe without a true beginning. The Big Bang singularity, that point of infinite density, it just disappears. It gets replaced by a quantum bounce. So picture the universe not as a single explosion from nothing, but as a cosmic heartbeat, a previous phase of contraction, everything collapsing. Then, as the quantum loops hit their maximum possible density, a repulsive force kicks in, a force born from the granularity of space itself. It's like stretching a rubber band to its absolute limit. There's a moment of maximum tension, and then it doesn't break. It snaps back, but with a new, powerful energy. That snap is the bounce, the start of our expanding universe. And the key is that repulsive force from the quantum geometry doesn't just vanish after the bounce. Its echo can linger. It can persist across billions of years, showing up as a gentle, residual pressure. A pressure that drives acceleration. So dark energy in this picture isn't a new substance. It's a memory, a fossil from the universe's quantum origin. A leftover push from the moment space rebounded. Pioneers like Abhay Ashtekar showed how this framework naturally avoids the infinities of the classical Big Bang. There's no point where the physics breaks down, just a transition, a turning of the cosmic wheel. This idea makes predictions. The quantum bounce would have imprinted specific patterns on the oldest light, the cosmic microwave background. Subtle swirls and ripples that future observatories might detect. It also suggests a different fate. If the acceleration we see is this fading echo, it might not last forever. The repulsion could gradually dissipate as the universe expands, leading not to an eternal, lonely expansion, but maybe to another turn of the cycle. This perspective does something more radical. It suggests that time itself, as we feel it passing, might not be fundamental. In the quantum geometry, time could be an emergent property, a consequence of the changing relationships between these loops. So we're left with a question. Is the force accelerating the cosmos today the final whisper of a previous cosmic era? Are we living in the long, fading afterglow of a quantum bounce? This idea ties the largest mystery to the smallest possible scales. It suggests that to understand where we're going, we must first understand what came before. And what if that before was not a beginning but a continuation? Gravity could be an illusion, just a side effect. That's the ninth idea, emergent gravity. The force that holds planets, that bends light, it isn't fundamental. It emerges like temperature. You can't point to one molecule and say, that's temperature. Temperature is a collective thing, a story told by countless parts, and gravity, this theory says, is the same. It's a story told by the microscopic bits of information that make up spacetime. Eric Verland gave it a form, entropic gravity. Entropy is disorder, the number of ways things can be arranged, and it always increases. Verland said what we feel as gravity is an entropic force. The universe's tendency toward disorder. Picture a holographic screen, the boundary of a region. On that screen, tiny bits of information like pixels. When a massive object is near, it displaces those bits, changes the arrangement, and entropy's tendency to increase creates a force pulling things toward the region of higher entropy. That pull is gravity. It's not a force from a particle. It's a statistical drift, like a crowd shifting, creating a current. Now take that to the whole cosmos. If gravity emerges from information on boundaries, then the universe's acceleration, dark energy, might emerge from the same principles. As the universe expands, the cosmic horizon grows. The information content changes, its possible arrangements change. That changing information landscape could generate a pressure, a push that looks like dark energy. The universe isn't driven by a mysterious substance. It's computing its own expansion, rearranging its fundamental bits, and that reorganization manifests as acceleration. Think of a vast, calm lake. The water seems smooth, but dip your hand in and move it. The water pushes back. That resistance isn't fundamental. It emerges from trillions of molecular collisions. In emergent gravity, the smooth spacetime of general relativity is that lake. Gravity and acceleration are the pushback, emerging from the underlying quantum information. It's a breathtaking reduction. It suggests all of physics at its core is information processing. Even constants like the strength of gravity could, in principle, vary. If the underlying information structure changes, but does this story match the detailed script of our universe? The challenge is making precise, testable predictions. Predictions that align with our cosmological data. Models of emergent dark energy must reproduce the exact rate of acceleration we measure, the specific way galaxies cluster, the subtle patterns in the cosmic microwave background. So far, crafting a model that passes all these tests is a formidable hurdle, yet the idea's power is undeniable. It reframes our deepest questions. We're not asking what dark energy is made of. We're asking what computation the cosmos is running. The force shaping the fate of everything might be a shadow cast by the slow, deep processing of information at the edge of reality. The rules of physics might not be fixed. That's the 10th idea. The constants of nature, the speed of light, the strength of gravity, they're supposed to be bedrock. The numbers that define reality, but they might not be. They could drift slowly over cosmic time, and if they drift, that variation could rewrite the history of expansion. It could create the illusion of dark energy or replace it entirely. This thought isn't new. Back in the 1930s, Paul Dirac noticed something. He compared huge cosmic numbers, the ratio of electrical force to gravity between a proton and an electron, and he compared that to the age of the universe in fundamental units. They were roughly the same immense size. He didn't think that was a coincidence. He proposed his large number hypothesis. He suggested these numbers were related because the fundamental constants were slowly changing as the universe aged. The constants were in tune with the scale of the cosmos. That was the seed. Modern theories give that seed new forms. They often link varying constants to extra dimensions. In some models, as extra dimensions evolve, their size influences the constants we measure here, or a new cosmic scalar field, something like Quintessence, could be slowly shifting. And as it shifts, it tweaks the values of nature's forces. John Barrow spent decades on this. He showed how a changing gravitational constant could alter the expansion rate in a specific way. If gravity was stronger in the past, it would have pulled matter together more fiercely early on. Then, as it weakened, its grip would loosen. From our perspective, that loosening could look like a new repulsive force taking over. It would mimic dark energy. The universe isn't accelerating because of a new energy. It's accelerating because the old force, gravity, is fading. To test this, you look for fingerprints of change. One way is with atomic clocks, incredibly precise devices that measure time based on atomic vibration. If the fine structure constant which governs electromagnetism were changing, the tick of these clocks would drift over years. Scientists compare different types of atomic clocks, watching for any subtle divergence. Another way is to look back in time. We do that with quasars. Brilliant beacons from the early universe. Their light travels for billions of years to reach us. It passes through ancient clouds of gas. Atoms in those clouds absorb specific colors of the quasar's light. The absorption pattern is a barcode. It tells us the exact values of the fundamental constants back when that light was absorbed. By comparing barcodes from quasars at different distances, different eras, we can see if the constants have shifted. So far, evidence suggests any change is extraordinarily small. The constants appear constant to very high precision, but the search continues because the implication is staggering. It means the cosmos is not just expanding within fixed rules. The rules themselves are part of the story. They are characters that evolve, so we're left with a question. What if the game isn't just being played on a larger board, but with rules that are slowly being rewritten? This vision of a mutable cosmos where the foundations themselves are in flux leads to an even wilder thought. What if our universe isn't alone? What if it's brushing up against others, and that contact is changing everything? The cosmological principle is this big assumption we all use. It says the universe is smooth on the largest scales, uniform, no special place, no special direction. That's the foundation. It's why we can take a few measurements and apply them to everything. But what if that's wrong? What if the universe isn't smooth? What if it's lumpy and we're in a unique spot to see it? That's the idea of the inhomogeneous universe. It suggests dark energy might be an illusion, a cosmic mirage, just from our particular vantage point. Think of the cosmos not as a uniform sea, but as a sponge. A vast sponge, immense filaments of galaxies. They weave through space, surrounding these titanic voids, regions nearly empty of matter, hundreds of millions of light years across. We live in the Laniakea supercluster, a dense knot in that cosmic web, and around us there are voids, like the local void, a relative emptiness, and gravity works differently in these places. In an overdense knot, gravity's pull is stronger. It slows the local expansion. In a vast underdense void, there's less matter to pull inward, so the space within the void expands faster. Faster than the denser surroundings around it. It's like judging the ocean's tide from a single wave. If you were floating on a massive, slow-moving swell, you might think the whole ocean was calm. Even as a fierce tide raged somewhere else, cosmologists explore this, 6e resonon, through a concept called backreaction. The idea is these lumps and voids aren't just minor wrinkles. They actively change the average expansion rate. When you try to describe it all with simple, smooth equations, you take the true, lumpy universe, you average it out mathematically to fit our smooth models. And an extra term appears in the equations. That term looks exactly like dark energy, a statistical artifact, not a physical substance. The acceleration we measure wouldn't be a new force. It would be a miscalculation, a failure of our smoothing procedure to capture the true dynamics of a clumpy cosmos. The debate is fierce. Proponents of the standard model argue the structures exist, but their effects are too small. Too small to account for the measured acceleration. They point to sophisticated computer simulations of the cosmic web. When these simulations include general relativity and all the observed matter, they still need a cosmological constant. To match the real universe's expansion, the backreaction effect, they say, is subtle, a correction, not the main driver, but the inhomogeneous universe idea strikes deeper. It challenges the cosmological principle itself. It asks if we've been too quick to assume uniformity. If this is correct, then our entire cosmic narrative changes. From the Big Bang to dark energy, it all needs to be reinterpreted from a perspective that acknowledges we are not at a typical point. We are observers embedded in a specific, complex structure. And that location shapes everything we see. Could the greatest mystery be a flaw in our averaging? Could the force accelerating the cosmos just be the ghostly imprint of vast, empty voids? Stretching the space around us, this idea doesn't just offer a new solution. It forces a question about the very lens we use to view reality. And if that lens is flawed, what other illusions might we be seeing? Phantom energy, that's the idea. It's a form of quintessence, but a specific one. The equation of state, the relationship between its pressure and density, isn't just negative. It's less than -1. That one change, that small mathematical tweak, it changes everything. For ordinary dark energy, the energy density stays constant as the universe expands. For phantom energy, it does the opposite. It increases, the universe gets bigger, and this stuff gets stronger, more potent. It's a feedback loop, a cosmic one with no off switch. The repulsion feeds on itself. As it pushes space apart, it gains strength, and with more strength, it pushes harder. This acceleration isn't gentle. It's exponential, it runs away. The result is what they call the Big Rip. First, the force grows strong enough to overcome gravity on the largest scales. Galaxy clusters fly apart, they're lost to each other. Then, as the phantom energy density soars, it targets individual galaxies. The Milky Way would be shredded. Stars flung into the accelerating dark, but it doesn't stop there. The force turns inward. It attacks solar systems. Planets are ripped from their stars. Then it comes for the planets themselves. Earth would be torn apart. Mountains, continents, the rock itself would fly into dust, and still it intensifies. It would overcome the nuclear forces holding atoms together. Nuclei would disintegrate. Finally, at a finite moment in the future, the scale factor, the very metric of spacetime, would become infinite. In a finite time, spacetime itself would rupture, the fabric of reality torn apart, a complete dissolution of everything. Cosmologist Robert Caldwell helped pioneer this model. He's called it speculative but a necessary exploration. We ask what's possible within the equations. Phantom energy is a reminder. A negative pressure is a profoundly strange thing. It can lead to futures far more extreme than a quiet, lonely expansion. We can test for it. The model predicts a specific acceleration history, slightly faster than the standard model. Current data from supernova and the cosmic microwave background, it tightly constrains the equation of state. So far, it's consistent with -1. The cosmological constant, the data doesn't yet show the sign of a value less than -1, but the error bars have room. Future observatories will shrink those uncertainties. They'll tell us if our universe is on a phantom path, or if this idea remains a thought experiment, a lesson in how delicate the cosmic balance might be. One decimal point in a parameter could decide between eternal expansion and absolute oblivion. It forces a question. Are we just reading the early chapters of a story that ends in total disintegration? The bullet doesn't need gunpowder. Its own motion is the engine. That's the 13th idea. K-essence, kinetic essence. It builds on quintessence but with a twist. Dark energy isn't a field sitting in some high-energy state. It's a field driven by its own motion, its kinetic energy, its raw speed through the cosmic landscape. In the equations, you write a non-standard kinetic term in its Lagrangian. That's the mathematical description of the field's energy. Instead of the usual simple term, like a rolling ball, you write something more complex. Something that changes how the field responds to the expanding universe. Think of a regular particle like an electron. Its kinetic energy comes from how fast it's moving, and it's always a positive, normal contribution. But in K-essence, the field's kinetic energy can become the dominant thing, the strange thing that generates negative pressure. It's as if the field's own velocity creates a kind of anti-gravity lift. A cosmic bullet whose sheer speed generates a repulsive force. Christian Armendariz Picone and others developed this to solve a key problem, the tracking problem. How does a dark energy field know to hide for most of cosmic history, only to emerge and dominate now? In K-essence models, the field can do this naturally. In the early radiation-dominated universe, the field's behavior is locked to radiation. It tracks it. Its energy density falls at the same rate. Then, when matter takes over, the field smoothly switches. It begins to track the matter density. It hides in plain sight, mimicking the dominant component for billions of years. Only recently, as the universe's density drops below a critical threshold, does the field break free. Its non-standard kinetic term kicks in. Its energy density slows its decline or even becomes constant, and it takes over. It becomes the dominant force driving acceleration. That tracking behavior is the elegant escape from fine-tuning. The field doesn't need its initial conditions set with impossible precision. It naturally follows the lead of the universe's dominant energy, waiting for its moment. There's another strange feature. K-essence can, under certain conditions, behave like a pressureless dust, a kind of dark matter. It can clump. So in this picture, the dark sector, both the glue and the propellant, could be unified again. Not as a Chaplygin gas, but as a single, dynamic field. A field whose kinetic properties determine whether it acts as clustering matter or smooth, repulsive energy. The question becomes profound. Is the vacuum alive with a kind of hyper-fast, frictionless motion? A fundamental restlessness of space itself that only manifests as a push when the cosmos grows quiet enough. This vision blends fluid dynamics with fundamental physics. It suggests the cosmos isn't just filled with stuff, but with currents, invisible currents whose speed dictates the fate of everything. And if the vacuum has currents, could it also have textures? Could there be cosmic defects frozen into the fabric of reality, left over from its fiery birth? The speed of light is the limit, but there's a loophole in the physics. The 14th idea calls dark energy a tachyon field. Tachyons are these hypothetical particles. They'd always move faster than light. They can't slow down to our speed. We've never seen one. But the math for a tachyon field gives you a model for cosmic acceleration. It's not about literal particles, it's a scalar field, a kind of cosmic fluid. It follows these peculiar equations. Its main feature is an inverted potential. Picture a ball on a hill. Normally, the ball rolls down. It gains kinetic energy from the height. For this field, the hill is upside down. It's more like a valley that flattens out. The field starts at the top of that inverted slope, a point of unstable equilibrium. Then it begins to roll, but as it rolls, the slope gets shallower. The field's kinetic energy grows in a specific way. Its pressure turns negative, deeply negative, while its energy density drops slowly. That combination creates accelerating expansion. It's like the universe's vacuum is a ball rolling down an infinite, ever-flattening hill, gaining a repulsive momentum from the shape of the terrain. This model fits naturally in string theory. In the dynamics of D-branes, these are membranes where strings can end. In some pictures, our universe is a D-brane. And these branes can be unstable, they can decay. The Tachyon field describes that decay process. The rolling of the field is the brane relaxing to a more stable state. The energy released in that slow, cosmic relaxation could be what we see as dark energy. So the universe's acceleration might be a side effect, a relic from a stringy process near the dawn of time. The universe settling into its seat, and the lingering motion from that settling is pushing everything apart. A major challenge for any Tachyon model is avoiding quantum instabilities. An inverted potential is tricky. It can lead to runaway fluctuations that could make the whole idea fall apart. Theorists like Ashok Sen have worked to show how, within string field theory, these instabilities can be controlled. The Tachyon condensation process can be stable. It leads to a new vacuum state. Our universe might exist in that new vacuum, and the energy of that vacuum state is our cosmological constant. This ties it back to the very first solution, but with a dramatic origin story. The cosmological constant isn't just a number. It's leftover energy from a topological transformation of reality's fabric. A cosmic defect that smoothed itself out, leaving behind a constant push. Could dark energy be the final sigh of a decaying brane? Are we living in the aftermath of a higher dimensional stabilization? This vision is elegant. It unifies the largest scale observation with the smallest scale theory. The fate of galaxies is written in the math of vibrating strings and decaying membranes. It suggests the answer to our biggest mystery might not be found by looking deeper into space, but by understanding the topological shape of reality itself. And if the universe's structure can have defects that smooth out, could it also have defects that persist forever, frozen cracks in spacetime from its earliest, most violent moments? The early universe had a kind of symmetry, a single force, then it expanded and cooled, and that symmetry broke. It happened in stages, like water turning to ice. And when a symmetry breaks like that, it can leave marks, imperfections frozen into reality itself. These are topological defects, they aren't matter. They're more like knots or walls or strings in the fields of space, wrinkles you can't smooth out. Cosmic strings are the most well-known. They're like one-dimensional cracks. Infinitely thin but incredibly dense. A loop of this string, thinner than a proton, could have the mass of a mountain range. They'd stretch across the cosmos, vibrating. If one passed through Earth, it would create a double image of everything behind it, a perfect lens. Then there are domain walls, two-dimensional sheets. They divide space where a field settled into different states. A domain wall moving through our solar system would be a disaster. Its gravity would disrupt every orbit. And textures are three-dimensional knots, twists in the field, more subtle, but they could still shape how the cosmos evolved. For a long time, cosmologists saw these defects as a problem. They'd create too much chaos, distorting the ancient light in ways we don't observe. So the standard model assumes a smooth, early universe, no defects. But what if a certain kind of defect network survived? Not the chaotic kind from old theories, but a frustrated network, a tangle that can't annihilate. It reaches a scaling solution. As the universe expands, the network stretches and rearranges, but its overall energy density stays constant, and this is the key. A network like that, of frustrated strings or a lattice of walls, can have negative pressure. Its equation of state can mimic dark energy. The persistent tension in these frozen wrinkles creates a constant, repulsive push. Imagine a carpet laid over a bumpy floor. You try to smooth it, but some wrinkles are locked in. They persist. Now put a toy car on that carpet. The persistent upward push from the wrinkle underneath makes the car roll away. It looks like a repelling force, but it's just the frozen geometry of the landscape. In this model, dark energy is that landscape, the fossilized wrinkles from the universe's first moments. A classical structure woven into space, not a quantum property of the vacuum. This idea comes from grand unified theories. When the strong force split from the electroweak force, that phase transition could have created such a network. Theorists like Tom Kibble worked out the math for how these defects form. The challenge is building a model where the network's energy density is exactly the tiny value we see for dark energy. Too dense and it would have torn structures apart long ago. Too sparse and it wouldn't matter. Observations constrain this tightly. The cosmic microwave background is extremely smooth. Any defect network would imprint specific patterns, distinct hot and cold spots, or subtle twists in the light's polarization. Satellites have mapped this ancient light in incredible detail. So far, no signature of a classical defect network has been found at the level needed to drive acceleration. The data favors a perfectly smooth, homogeneous dark energy. But the search continues at finer resolutions. Could a subtle, ultra-low energy network be hiding in the noise? A ghostly lattice from the grand unification epoch, its gentle push only now becoming dominant. This offers a stark contrast. It's not quantum vacuum energy. It's not a changing field. It's architecture, the frozen-in skeleton of a younger, hotter universe. A cosmic fossil exerting its will on the present. The question it leaves us with is architectural. Is the accelerating universe built on a framework of ancient, invisible scars? Supersymmetry imagines a kind of perfect balance. You'd have a partner for every matter particle and a partner for every force particle. An electron gets a selectron. A quark gets a squark, a photon gets a photino. It's this beautiful doubling of everything, and it gives you something. In a perfect, unbroken supersymmetric world, the vacuum energy from a particle and its partner would be exact opposites. They'd cancel. The quantum noise of empty space would add up to zero. The cosmological constant problem would just go away. Space wouldn't have any built-in energy pushing it apart. But we don't live in that perfect world. We haven't seen any of these superpartners. If they're real, they have to be much heavier, so supersymmetry is broken. That perfect cancellation is ruined, and when a perfect symmetry breaks, it leaves something behind, a remnant. That tiny mismatch from the cancellation that's no longer perfect could be the source of a small, positive vacuum energy. That leftover, the echo of a broken symmetry, could be our cosmological constant. Steven Weinberg saw this as a naturalness problem. Why is the leftover so incredibly small? The energy scale of supersymmetry breaking, if it's tied to the weak force, is 1 trillion times bigger than dark energy's scale, so the leftover should be enormous. Not the tiny whisper we see. To get the number we observe, the initial cancellation had to be unbelievably precise. Then the breaking had to be tuned just right to leave this minuscule residue. It feels like we've traded one fine-tuning problem for another, and that leads to a deep, unsettling thought. Maybe this tuning isn't an accident in our one universe. Maybe it's a selection effect. In a vast multiverse with countless universes each having different constants and vacuum energies, most would have values that make galaxies and stars and life impossible. We could only find ourselves in one of the rare, finely tuned universes, where the leftover from broken supersymmetry is just small enough to allow us to exist, but not zero. So dark energy, in this view, isn't explained by a fundamental law. It's explained by us being here to see it. It's an environmental necessity. This idea ties the fate of the whole cosmos to ultra-high-energy particle physics. It suggests the answer to why space is accelerating isn't written in the galaxies. It's in the failed search for superpartners in our colliders. The accelerating universe becomes a clue, pointing to a symmetry that once was perfect and whose broken pieces now gently push everything apart. The multiverse gives a radical answer to fine-tuning. It doesn't solve the puzzle, it dissolves it. If our cosmos is just one bubble in an infinite sea of universes, each with random laws, then our gentle dark energy isn't strange. It's inevitable. We could only find ourselves in a bubble where the numbers allow stars and planets, observers. That's the anthropic principle. It doesn't explain why the constant has its value. It explains why we see that value. String theory's landscape gives a mechanism. The theory doesn't predict one unique vacuum. It predicts a stupendous number. Maybe 10 to the 500 different vacuum states, each with a different cosmological constant. Eternal inflation, space inflating forever, gives birth to countless bubbles from this landscape. Each bubble is a separate universe crystallizing with a random set of constants. Ours is one, a rare one, where the vacuum energy is small but not zero. Proponents like Leonard Susskind call this a Copernican revolution in scale. We're not at the center of space, and our universe isn't special in the cosmic landscape. It's just habitable. Critics see a retreat. Does this explain dark energy or just explain it away? By making the constant a random environmental variable, the multiverse moves it. From fundamental physics to statistics, it becomes a feature of our local cosmic address, not a law that triggers deep philosophical debate. If a theory predicts everything, does it predict anything? Can a statistical, anthropic argument ever satisfy a search for cause? Yet its power is undeniable. It reframes the greatest fine-tuning problem, not as a flaw in our theories, as a selection effect in a reality far vaster than we dreamed. The gentle push accelerating our galaxies might be a signature, our bubble's particular birth. A cosmic lottery ticket that allowed us to be here, wondering about it. This statistical view leads to a more profound question. If universes bubble up from a quantum landscape, could our entire cosmos be a quantum fluctuation? A single event from nothing. The universe could be a self-replenishing engine. That's the 18th idea. The expansion of space might coax new matter into existence. From the quantum vacuum, not all at once but continuously, a slow drizzle of particles from the fabric of reality. It's called the creation of cold dark matter model. CCDM. It revives an old concept, the steady-state theory. Fred Hoyle, Thomas Gold, Herman Bondi. A universe with no beginning and no end. As it expanded, new matter was created to keep the density constant. That model fell out of favor with the cosmic microwave background, the echo of a hot Big Bang, but the idea of continuous creation never fully disappeared. It's been reinterpreted within a universe that does have a beginning. In this model, the creation isn't ordinary matter, it's cold, dark matter particles. And this creation acts as a source term in Einstein's equations, an extra input, a mathematical term for new mass appearing as space stretches. That source term can alter the expansion. In the right balance, it can produce acceleration without a traditional cosmological constant. The push doesn't come from a mysterious energy. It comes from the act of creation itself. Expanding space generates mass, and that generation modifies the geometry, allows for acceleration. It's a feedback loop between the cosmos and its contents. Picture a moving sidewalk. The sidewalk is expanding space. The motion of the sidewalk, its stretching, causes new travelers to materialize. These new passengers add their weight. But in cosmology, this added mass can have an effective negative pressure. It can make the sidewalk want to stretch even faster. The engine of expansion is also the factory for its own fuel. Could dark energy be this process, the universe gently birthing new dark matter from the quantum froth, that birth providing the push for further expansion? This idea links two problems: what dark matter is and why the universe accelerates. They become two sides of a single coin, the creation process. Some versions lead to a profound possibility. A cyclic cosmos. If creation balances expansion just right, the universe might avoid a final heat death. It could reach a turning point where the created matter's gravity halts the expansion. Reverses it, leads to a contraction, a crunch, potentially a new bounce, a new cycle. So the gentle acceleration we see today wouldn't be a one-way ticket to emptiness. It could be part of a long, slow breath, an inhalation of quantum potential, followed by an exhalation of gravitational collapse. This vision transforms dark energy from an end into a transition, a phase in an eternal rhythm. The question it leaves is philosophical. Is the cosmos a once-and-done explosion, or is it a living, breathing entity, constantly renewing itself from the quantum depths of nothingness? A universe that breathes needs a rhythm. The 19th idea is about eternal return. A cosmos with no real start, no real finish, just cycles, expansion, then contraction, then a bounce. In that picture, dark energy isn't the end, it's an intermission. A pause that resets everything. Imagine two huge sheets of reality floating parallel in a higher dimension. They're called branes. Our whole universe is on one of them. And they drift. Over eons, they move toward each other. They don't merge, they collide. A smooth, elastic, titanic impact. That collision pours an immense amount of energy into our brain. It ignites a hot, dense, expanding universe, a big bang, but it wasn't a singularity from nothing. It was a rebirth from a previous cycle. That's the Ekpyrotic universe. From Paul Steinhardt and Neil Turok, in the cycle, the universe expands and cools, stars form, galaxies evolve, and eventually dark energy takes over. The vacuum energy, or a quintessence field, drives accelerated expansion. That phase is crucial. It stretches the cosmos to an incredible smoothness. It flattens it. It dilutes all the entropy, all the debris from the cycle before. It wipes the slate almost clean. It prepares a pristine, uniform state. Then, in the vast emptiness of that accelerated epoch, the branes can move together again. Drawn by a force between them, they collide and the cycle starts over. Dark energy in this story is the cosmic janitor. Its job is to sweep the universe out, to make it ready for the next bounce. A different kind of cycle comes from Roger Penrose. Conformal cyclic cosmology. It doesn't involve a crunch or a bounce in the usual way. Instead, it uses a deep mathematical symmetry. In the far, far future, the universe has expanded to near nothingness. All particles decay to their lightest states. All structure is gone. In that cold, empty, featureless state, the universe loses its sense of scale. A single photon flying through infinite emptiness experiences no scale at all. That distant future state, Penrose argues, becomes mathematically identical to the smooth, hot, dense state of the Big Bang. Through a conformal transformation, a rescaling of geometry, the end of one cycle becomes the beginning of the next. The universe forgets its size but not its geometry, and in this model, the accelerated expansion from dark energy is the essential process that erases information. That smooths everything out to that timeless, scale-free state. It is the great eraser, allowing the cosmos to be reborn from its own ashes. These visions are staggering. They replace a linear timeline with an Ouroboros, a cosmic snake eating its own tail. Dark energy gets demoted from a mysterious, dominating force to a functional part of a grander machinery. Its purpose isn't to lead us to oblivion, it's to enable renewal. Is our accelerating epoch just a deep, slow breath before the next cosmic heartbeat? Are we living in the calm, expansive sigh before a new beginning? That recontextualization is powerful. It turns a mystery about our end into a question about our place in an eternal story. The gentle push we measure in distant supernova might be the silent, steady preparation for a rebirth we'll never see. It suggests creation isn't a one-time event in the distant past. It's a recurring feature of reality, and the force we call dark energy may be its quiet, diligent architect. A massless graviton travels forever. That's Einstein's gravity. The particle that would carry the force has no rest mass. It moves at light speed, so the range is infinite. But suppose that's not quite right. Suppose the graviton has a tiny mass. That's the idea, massive gravity. It's a direct challenge. If the graviton has mass, gravity changes. It becomes a short-range force. Its influence decays faster with distance. On solar system scales, the decay is minuscule. You wouldn't see it, but across the distance between galaxy clusters, that tiny decay adds up. Gravity gets weaker over those cosmic distances. And from where we are, weaker gravity on the largest scales looks just like a repulsive force. It looks like dark energy. The history is a minefield. The first attempt was the Fiers-Pauli theory from the 1930s. It seemed straightforward, but it had a fatal flaw, a ghost, a mathematical instability that made the theory predict nonsense. For decades, massive gravity was seen as a dead end, a nice idea that couldn't work. Then, in the 2000s, a breakthrough. Claudia de Ram, Gregory Gabadads, and Andrew Tolley. They found a way, the DRGT theory. It builds the terms in the equations with exquisite care. It cancels the ghost. It gives the graviton a mass without breaking the universe. But a new problem emerged. If you just turn on a massive graviton, its effects in the solar system would be huge. It would predict wrong orbits. The theory would be dead on arrival. So you have to hide it. The answer is the Weinstein mechanism, named for Arkady Weinstein. It's a screening effect. Think of gravity as a wave in a pond. If the water is pure and light, the wave travels far. That's massless gravity. Now make the water thick with honey, viscous. A wave in that honey dissipates quickly. Short range, that's massive gravity. But the Weinstein mechanism says the viscosity isn't constant. Near a massive source like the sun, the gravitational field is so strong it thins the effective honey. It screens the massive effects. Within a certain radius, gravity behaves exactly as Einstein said, perfectly. But go beyond that radius, into the cosmic deep where fields are weak and the honey thickens. The graviton's mass asserts itself. Gravity weakens. This radius is the Weinstein radius. For the sun, it's enormous, far beyond the solar system. So all our local tests are safely inside the screen, seeing normal gravity. But the cosmos at large is outside, seeing the modified, weaker force. It's a masterful sleight of hand, a theory that changes everything but hides the change in plain sight. It's the most sophisticated attempt yet to directly alter Einstein's framework on cosmic scales. Could the accelerating universe just be a sign that the graviton has a tiny weight? That gravity, the force that shapes everything, finally fades across the great voids. This idea doesn't just offer an alternative to dark energy. It asks us to weigh the messenger of gravity itself. Einstein's equations treat gravity's strength as a fixed number, but that number might not be fixed. It could be a dial, and the dial could be turned by something else. That's Scalar-Tensor theory. It's a direct generalization of general relativity. You add a new field, a scalar field, that fills all of space, and this field doesn't just sit there. It sets the strength of gravity. Where the field is stronger, gravity is stronger. Where it weakens, gravity weakens. So you get a dance, a back and forth between space-time geometry, the tensor part, and this scalar field. They're coupled, they influence each other. The expansion of the universe affects the scalar field, and the scalar field's evolution changes how gravity works, which changes how the universe expands. It's a cosmic feedback loop. The early version is Brane's Dicke theory from the 60s. Karl Brane and Robert Dicke were motivated by Mach's principle, the idea that inertia here is influenced by all the mass out there. In their theory, the gravitational constant isn't constant. It's the reciprocal of this dynamic scalar field. So as the universe expands and matter thins out, the scalar field evolves. Gravity's strength could slowly change over cosmic time. For a long time, solar system tests constrained Brane's Dicke. Planetary orbits, especially Mercury's, demanded the field be very weakly coupled. It had to look almost like standard gravity, but on cosmological scales, the story is different. A scalar field evolving over billions of years can, later on, behave like dark energy. As the field rolls toward its minimum, its energy density can become dominant. Its pressure can turn negative. The late-time acceleration of the universe could just be the scalar field settling down. Its changing value provides that gentle push. Modern extensions go further. The most general class is Horndesky theory. Gregory Horndesky worked it out in the 70s, the most general scalar tensor theory with second-order equations of motion. It was largely forgotten, then rediscovered as a framework for dark energy and modified gravity models. Horndesky theory is a toolbox. It contains a family of interactions between the scalar field and curvature. These interactions can be tuned to produce specific cosmic histories. They can mimic a cosmological constant or produce dynamical quintessence. They can even screen modifications in dense regions like our solar system through mechanisms like the Weinstein effect. It's a rich playground. You can build models where dark energy interacts with dark matter, or where gravitational waves travel at a slightly different speed than light. That's a prediction you can test with events like neutron-star mergers. The philosophical shift is profound. In scalar tensor theories, dark energy isn't necessarily a separate substance. It's the kinetic and potential energy of the field that governs gravity itself. The force that binds the cosmos and the force that seems to be tearing it apart could be two sides of the same coin. Mediated by this one dynamic entity, the acceleration we see might be the gravitational constant very slowly finding its final value. This connects to the idea of varying constants, but gives it a dynamical mechanism. The field isn't just changing arbitrarily. It's changing according to an equation coupled to everything else. Testing these ideas means looking for subtle deviations from pure Einsteinian gravity. Does the strength of gravity measured in a lab match the strength inferred from galaxy motions? Does light bending around a massive cluster tell the same story as the orbits of stars within it? Future surveys will map the growth of cosmic structure and the bending of light across the universe. They'll search for the signature of this dance between the scalar field and geometry. They'll look for a telltale slip between how matter clumps and how space expands, a discrepancy that could signal a fifth force mediated by this field. So the question becomes unifying. Is cosmic acceleration a symptom of gravity's strength being set, not by a fundamental constant, but by a living, breathing field that is still finding its equilibrium? If so, then the force that holds our feet to the ground and the force that determines the fate of the cosmos are linked, dynamically linked in a way Einstein never envisioned. The universe isn't just expanding within a fixed gravitational framework. The framework itself is breathing along with it. The stage can't change size. In general relativity, spacetime is dynamic. It can stretch and bend. The stage can grow. But unimodular gravity asks something else. What if the total volume of the universe is fixed? It's an absolute and unchanging quantity. The theory gets its name from a mathematical condition. The determinant of the metric tensor, it measures local volume, is set to a constant. It's unimodular. That's a subtle restriction. You're not letting the fundamental volume element of spacetime change. Think of it as a canvas. The canvas has a fixed total area. It can't be made larger or smaller. But the painting on that canvas, the image of the universe, can still be stretched, distorted. Stars and galaxies can move apart. Space can expand in some directions, but it has to contract in others to keep the total canvas area constant. This constraint changes Einstein's equations. Deeply, the cosmological constant, lambda, is no longer a fundamental parameter you put into the equations by hand. It emerges as an integration constant. A constant of motion, a number that's not set by theory but by the initial conditions of the universe. It's determined by how the universe started. That's a radical shift. In the standard view, the cosmological constant is a fixed feature of the laws of physics, a number that just is. In unimodular gravity, it's more like the total energy of a closed system. It's set once at the beginning and then conserved. This could address the fine-tuning problem. Why is the cosmological constant so incredibly small? Maybe because the initial conditions of our universe just happen to select that value. It's not a law demanding a precise, unlikely number. It's a historical accident. A cosmic initial setting. Physicists like Steven Weinberg explored this connection, noted how it changes the philosophical weight of the problem. The stage is fixed. The actors and the scenery move within that absolute frame. The acceleration we see, the push of dark energy, would then be a consequence of that initial setting. It's the energy budget the universe was born with, playing out over 14 billion years. Could this subtle reformulation be the key? By insisting that four-dimensional volume is absolute, unimodular gravity recasts dark energy. Not as a mysterious substance, but as a memory of the universe's first moment. A single number, frozen into the cosmos at its birth, now gently urging every galaxy apart. It suggests that to understand the force shaping our future, we might need to understand the very first decision reality ever made. Gravity might have a memory. In Einstein's theory, the curvature at a point comes from the matter and energy right there. It's local, it's the here and now, but maybe that's incomplete. Maybe reality has a memory. The 23rd idea is non-local gravity. In these theories, the curvature at a point doesn't just depend on its immediate surroundings. It depends on the entire past history of the universe, or on distant regions all at once. Action at a cosmic distance, built into gravity's equations. To get there, theorists modify Einstein's equations. They add non-local terms. One of the simplest forms uses an operator, the inverse D'Alembert, acting on the curvature scalar. That's a mathematical way of saying the equations now include an average over the past light cone, over everything that could have influenced this point. It's like the universe keeps a ledger, a gravitational ledger, and entries from billions of years ago still affect the balance today. Think of a special elastic. Not a simple rubber band that snaps back based on how you're stretching it now. Imagine a material with a deep structural memory, like certain metals that, when bent, remember their original shape and try to return. Or like moss that holds the imprint of a stone long after the stone is gone. Non-local gravity treats spacetime like that. Its response to matter today is influenced by how it was stretched and curved in the distant past. By the echoes of the Big Bang, by the formation of the first galaxies. That accumulated history can generate an effective pressure, a pressure that, in today's low-density universe, acts to push. It looks like dark energy. Pioneers like Stanley Desir and Richard Woodard worked on these models. They showed how these non-local terms, these cosmic memory effects, could produce a late-time acceleration. Without a new field, without a cosmological constant, the math is complex. It involves integrals over the history of the cosmos, but the concept is physical. The universe's expansion today could be a reaction to its own traumatic birth, a long, slow relaxation from that initial, violent stretch. This adds a deep temporal aspect. Dark energy isn't just about what fills space now, it's about what happened to space then. The force accelerating galaxies might be a ghostly echo of the universe's infancy. A gravitational aftereffect, it suggests that time itself and history are active players, not just the static contents of space. Could it be that we feel the push of dark energy because the cosmos is still sighing from its first moment? That the acceleration is the universe remembering and responding to its own incredible beginning? This idea blurs the line between past and present. In the fabric of gravity, all moments might be connected. The fate of everything could be written not in a constant, but in the indelible memory of space-time itself. Space isn't silent. It has this quantum energy, virtual particles. They flicker in and out, a kind of foam. In a lab, you can see its shadow. You take two perfectly smooth metal plates. Uncharged, put them in a vacuum, extremely close together, and an invisible force pulls them together. That's the Casimir effect. It happens because the plates restrict the quantum fluctuations in the gap. Outside the plates, all wavelengths can exist, they froth, but between the plates, only certain wavelengths fit, like notes in a flute. That restriction means there's slightly more quantum pressure pushing on the outside than from inside the gap. The net result is an inward force, a pull from the vacuum. It's a small force, only measurable at microscopic distances, but it's real, the quantum vacuum asserting itself. Now take that idea and stretch it to the size of the cosmos. The 24th proposal asks this question. What if the universe is a kind of cavity? What if it has boundaries or a topology that restricts quantum fluctuations on the largest scale? Could a cosmic Casimir effect generate the repulsive pressure we call dark energy? In this picture, the observable universe is the gap between those plates. The boundary isn't a physical wall. It could be a topological feature, a shape to reality that forces quantum fields to vibrate in specific, resonant modes. Just as the plates forbid certain wavelengths, the cosmic topology would forbid the longest wavelengths. This changes the balance of the quantum vacuum energy. When you calculate the energy density of this restricted vacuum, you don't get that catastrophically large number. You get a finite, very small number. That leftover, the energy of the allowed quantum waves resonating through the cosmic cavity, could be our cosmological constant, dark energy as an architectural byproduct. The shape of space tunes the hum of the quantum vacuum. Extrapolating from a lab bench to the whole cosmos is a leap. The challenges are immense. The standard Casimir force is attractive. It pulls plates together. For it to be dark energy, it would need to be repulsive, a cosmic push. Theorists like Michael Bordag have explored configurations that could yield repulsion. If the boundary conditions are different, if the cosmic plates impose different rules on the fields, like Dirichlet versus Newman conditions, the sign of the force can flip. The math here is complex. Quantum field theory in curved spacetime with boundaries. It involves techniques like Z, a function regularization to tame the infinities. Another framework comes from Brane cosmology. If our universe is a three-dimensional brane floating in a higher dimensional bulk, its boundaries in those extra dimensions could act like the plates. The bulk constrains the quantum fields on our brane. The Casimir energy from those hidden dimensional boundaries could seep into our four-dimensional world as a constant, repulsive energy density. It's a haunting image. The force accelerating every galaxy might be a whisper from the edges of our reality in directions we can't perceive. The speculative nature is clear. We have no evidence the universe has such a topology or hard boundaries. The cosmic microwave background is smooth. It shows no signs of repeating patterns or reflections you might expect from a small, wrapped-up universe. Yet the idea persists. It connects two truths. The quantum vacuum has energy, and geometry dictates physics. Could the two be married to solve our greatest puzzle? Is dark energy simply the universe listening to its own shape and finding a note that pushes everything apart? This approach adds a layer of elegance. It suggests the answer isn't in a new substance or a changed law, but in the resonant song of nothingness played on the instrument of all space and time. The 25th idea is the action. It's a hypothetical particle, originally proposed to fix a symmetry problem in the strong nuclear force. That's the force that holds quarks together inside protons and neutrons. The math says the force should treat matter and antimatter differently in a specific way, but it doesn't. The action was introduced to restore that balance. It's a very light particle, and in doing that, it also becomes a natural candidate for dark matter. But then string theory comes in. It predicts not one action, but many. A whole landscape of them. They're called action-like particles, or ALP. They're everywhere. Each has a tiny mass and its own energy landscape. These aren't particles moving fast. They can form a coherent field that fills all of space, a field that oscillates but incredibly slowly. The period could be billions of years, and here's the link. If such a field is still slowly rolling down its potential, a slow roll, its energy density can act like a cosmological constant. It can be a form of quintessence, but one that comes from a specific particle. Think of a bell struck at the beginning of time. It's still ringing. The vibration is so deep and slow we don't hear it as sound. We feel it as a steady, gentle pressure filling the universe. That could be the action-like particle field. Its oscillations create an average energy density. With negative pressure driving the acceleration we see, this connects two worlds. It links the quantum world of particle physics symmetry problems, string theory, to the cosmic fate of the entire universe. The same framework that might explain proton stability could explain why galaxies are flying apart. Experiments are looking for these particles now. They search for very subtle effects. Because ALPs are so light and weakly interacting, they might convert to photons in strong magnetic fields. Experiments like ADMCS use powerful magnets and sensitive detectors in cryogenic chambers, listening for that faint whisper. Other searches look at the polarization of light from distant quasars, or for tiny irregularities in the cosmic microwave background that the field's oscillations might leave behind. So dark energy could be this cosmic hum, a vibration from an invisible particle field set in motion when the universe was young. The force accelerating the cosmos might not be a property of empty space. It might be the breath of a particle so light it barely feels like matter, a ghostly presence solving two great puzzles at once. The universe might have a fever. Not a temperature, but a kind of drive, a drive toward disorder. That's entropy. The second law says it always increases, and the cosmos is no different. It's the ultimate closed system, so maybe dark energy isn't a force or a field. Maybe it's a consequence of the universe's march toward maximum entropy. That's the 26th idea, Entropic Cosmology. It builds on emergent gravity, takes that thermodynamic view to its logical extreme. In this picture, the cosmic horizon, the boundary of what we can see, it isn't just a limit. It's a membrane. It holds information like a black hole's event horizon. The holographic principle says the maximum entropy the universe can hold is proportional to the area of that horizon. Not its volume. As the universe expands, the horizon grows, the area increases, so the maximum possible entropy increases, but the actual entropy inside is trying to catch up. It's always striving to reach that maximum, and that striving can generate a force, an entropic force. Think of a gas in a box with a movable piston. The gas molecules bounce off the piston. Their collective push is pressure, but from a thermodynamic view, that pressure is an entropic force. The gas expands because there are more ways for the molecules to be arranged in a larger volume. More disorder, the system moves toward higher entropy. Now replace the gas with the universe, replace the piston walls with the cosmic horizon. The expansion of space could be driven by a similar entropic push. The universe expands because that increases the maximum possible entropy on its boundary. Then you bring in the Casimir effect, that quantum pressure from restricted vacuum fluctuations. In entropic cosmology, the horizon itself imposes a boundary condition on quantum fields. Just as metal plates restrict wavelengths in the lab, the cosmic horizon restricts the longest possible wavelengths in the universe. That restriction alters the vacuum energy density at the boundary, so you have this combination: the thermodynamic drive from the horizon's growing area, plus a quantum Casimir-like contribution from the boundary restricting fields. Together, they can produce an effective dark energy term in the equations. The derivation is elegant. You start with the first law of thermodynamics. Energy conservation applied to the cosmic horizon. You treat it as a thermodynamic system with temperature and entropy. The entropy is given by the Bekenstein-Hawking formula. Proportional to the horizon area, the temperature is the Hawking temperature, inversely proportional to the horizon radius. When you apply energy conservation to this system, accounting for the work done by expansion and the heat flow across the horizon, an extra term appears. That term has the exact form of a cosmological constant. It looks like dark energy, but it's not a substance. It's a thermodynamic response, the universe's reaction to its own horizon's properties. This leads to a question: is the universe expanding simply to maximize its entropy? Is acceleration the most efficient path to the greatest possible disorder? In this view, dark energy is an emergent phenomenon, a side effect of the cosmos obeying the most fundamental law of thermodynamics. It contrasts sharply with dynamical field explanations. Like quintessence, there's no new particle, no evolving energy, just the old, reliable drive toward disorder playing out on the grandest stage. The implications are philosophical. They suggest the arrow of time and the fate of the cosmos are linked. The acceleration we measure isn't the cause of time's direction. It might be its most spectacular effect. The universe isn't being pushed by a mysterious force. It's sliding down the steepest slope of probability toward its final, quiet, maximally disordered state. The force we call dark energy could be the universe sighing as it settles into the configuration with the greatest number of possibilities, a thermodynamic destiny. Written not in particles or fields, but in the cold, beautiful logic of statistics. Neutrinos are these cosmic ghosts. Trillions pass right through you every second. They barely interact with anything. For a long time, we thought they had no mass at all. But then experiments showed they do have a tiny mass. They oscillate, they change flavor as they travel. That small weight means they actually make up a significant part of the universe's energy. But then there's this idea: what if that mass isn't a fixed number? What if it's part of a conversation? That's the idea of mass-varying neutrinos. In this picture, the neutrino's mass isn't constant. It's tied to a cosmic field. A scalar field, the same kind of field that could be quintessence, the dark energy. And as this background field evolves over cosmic time, it gently tweaks the mass. Tweaks the mass of every neutrino, and here's the crucial part. When you have a field coupled to matter like that, energy can transfer between them. So as the universe expands and cools, the neutrinos lose kinetic energy. They slow down, but with this coupling, some of that lost energy doesn't just vanish. It gets fed into the scalar field. It boosts the field's potential energy. It acts like a slow-charging battery. The fading energy from the neutrinos slowly charges the dark energy field, and that changes the expansion history in a specific way. It means the acceleration, the dark energy taking over, doesn't start until the neutrinos become non-relativistic, until they slow down enough for their mass to really matter. And that happens relatively late. It happens late in cosmic history. So this model naturally explains why dark energy only became important recently. The cosmos was waiting. It was waiting for the neutrino bath to cool to the right temperature. It needed these ghostly particles to shift gears first. And this creates a link, a direct link between the smallest scales and the largest. Experiments like DESI, the dark energy spectroscopic instrument, are mapping the expansion history now with incredible precision. They can measure the exact moment when acceleration began, and if that moment aligns with when neutrinos became non-relativistic, that would be a clue. A stunning clue. Meanwhile, neutrino observatories, places like Supersymmetry and/or the Future Dune experiment, they're measuring neutrino properties more and more accurately. They're looking for any hint that neutrino behavior changes over cosmological timescales. Any anomaly could be a signal of this dialogue, this cosmic dialogue. The beauty is the unity. It doesn't invent a new, separate dark energy. It uses something we know exists, neutrinos, and a mechanism we know can happen, field coupling, to produce the effect. These faintest particles become cosmic intermediaries. Their silent interaction with a hidden field could be the engine of acceleration. So you have this connection. The same particles that stream from the sun, from distant supernova, that barely notice our world, they might be in a slow dance with the fabric of space itself. And that dance could ultimately decide the fate of every galaxy. The key to the universe's expansion might be held in the changing weight of a ghost. The floor and the dancers aren't separate things. In Einstein's picture, the dancers, that's matter and energy, they tell the floor, which is space-time, how to curve. And then the floor tells the dancers how to move. It's a one-way conversation. Matter dictates the geometry, and the geometry dictates the motion. But then you think, what if the conversation goes deeper? What if the floor itself, its material, changes because of the dancer's steps? That's the core of F of R, T gravity. It's a bold extension of modified gravity. You remember F of R theories, where gravity depends on a function of curvature, R. F of R, T goes further. The gravitational action depends on both the curvature, R, and on T. T is the trace of the stress-energy tensor. It's a single number that summarizes the content, the pressure and density of matter and energy in a region. By making gravity a function of both R and T, you introduce a non-minimal coupling. Geometry and matter are now in a direct two-way dialogue. They influence each other's fundamental behavior. Think of it as a dance in a special hall. In Einstein's hall, the floor is rigid. The dancers move, the floor bends under their weight, and that guides their path. In F of R, T, the floor is made of a responsive material, like a smart, adaptive surface. When a dancer presses down, the floor doesn't just bend, its texture changes. It might become more elastic or more viscous right under their feet, and that change in the floor's nature then alters the force it exerts back on the dancer. It changes their next step. The dancers and the floor are co-creating the performance. Each step changes the stage, and the changed stage dictates the next step. Mathematically, this coupling introduces new terms into the equations of motion, terms that mix the derivatives of the matter fields with the curvature. When you apply these equations to the whole universe, to the homogeneous, isotropic cosmic fluid, these extra terms can behave exactly like an effective dark energy component. They can generate a repulsive pressure, a push that isn't from a new field or a cosmological constant. It emerges from the very fact that gravity cares about what matter is doing in a more intimate way. The acceleration of the universe could be a signature of this conversation, a sign that spacetime is listening to the cosmic matter and responding in a way that gently drives it apart. This differs sharply from pure F of R theories. In those, matter still moves on geodesics. The coupling is minimal. Here, the coupling is non-minimal. It means the conservation of energy and momentum, a sacred principle in standard physics, can be modified. Energy might not be conserved in the usual way because it is trading off with the geometrical sector. This has profound implications. It can affect structure formation. It can alter how perturbations in the early universe grow into galaxies. It offers new ways to address cosmic tensions, like the observed clustering of matter versus the standard model's prediction. The motivation is a drive for completeness. If we're willing to modify the geometry part of Einstein's equations, why not also examine the coupling between geometry and matter? Perhaps the true theory of gravity on all scales involves this deeper entanglement. Dark energy, in this view, is not a separate entity. It is the dynamical outcome of spacetime and matter in a continuous, direct embrace. The force accelerating every galaxy might be the sound of that conversation, a cosmic dialogue written into the laws of motion themselves. This represents the cutting edge of gravitational model building, a testament to the creativity unleashed by a single, stubborn observation that the universe is flying apart faster than it should. Perfect symmetry is a beautiful idea, but nature tends to break it. In quantum physics, there's a symmetry called conformal symmetry. It means a system looks the same at all scales. You zoom in, you zoom out, the physics stays the same. It's perfectly balanced, but in our real universe, when you put quantum fields into curved spacetime from general relativity, that perfect symmetry can't survive. Quantum effects shatter it, and when it breaks, it leaves something behind, a quantum footprint. That footprint is called the trace anomaly. In the math, there's a quantity called the stress-energy tensor. It describes the density and flow of energy and momentum. For a classically conformal field, one with that perfect scale invariance, the trace of this tensor is exactly zero. But when you do the full quantum calculation, accounting for the wild fluctuations in curved space, that zero becomes something else. It becomes a small, finite number. That's the anomaly. The trace is no longer zero. The perfect scale has a tiny, persistent imbalance. It's like the constant quantum jitter of empty space leaves a faint mark on reality. This anomaly adds a term to cosmology's equations, a term that, under the right conditions, acts like a cosmological constant or like a dynamical form of quintessence. Its energy density can be constant or it can evolve. Work by theorists like Alexei Starobinsky showed this trace anomaly, from combining quantum fields and gravity, could drive accelerated expansion. In this view, dark energy isn't a new field or modified gravity. It's a quantum correction, a side effect of trying to make quantum mechanics and general relativity talk to each other. The push accelerating the universe could be the unavoidable result of quantum fields realizing they live on a curved, dynamic stage. Their perfect symmetry breaks, and the energy released manifests as a gentle, repulsive pressure. To make it tangible, think of a perfectly still, mirrored pond. It reflects the sky without distortion. That's conformal symmetry. Now cast a single, tiny pebble into its center. The impact creates a ripple. The ripple spreads, distorting the perfect reflection. The pond is no longer scale invariant. The ripple defines a scale. The trace anomaly is that ripple. The pebble is the quantum effect of curved spacetime, and the energy carried by that spreading ripple as it fills the entire pond could be the dark energy we measure. It's a relic of the moment quantum fields realized the cosmos wasn't a flat, static stage. This idea ties the largest mystery directly to the most fundamental tension in physics. The interplay between the quantum and the classical, the gravitational and the particulate. It suggests dark energy might be the first macroscopic signature of quantum gravity. Not in tiny strings or extra dimensions, but in the subtle accounting of energy in a universe where nothing, not even nothingness, is perfectly symmetric. Could the force separating galaxies be the echo of a symmetry broken when the first quantum field stirred in the newborn cosmos? A cosmic receipt for a dynamic, evolving universe, paid for with the last vestiges of perfect, scale-free emptiness. The biggest mystery might not be what dark energy is. It might be whether it's even real. We've looked at dynamic fields, decaying branes, quantum whispers. We've questioned gravity, rewritten constants. But this last idea, the 30th one, is the most radical. It says dark energy isn't a physical thing. It's an illusion, a sign that our whole cosmological framework has a fundamental error. This isn't a specific model, it's a meta-solution, a call to step back and question the very premises of the problem we're trying to solve. For centuries, astronomers watched the planets wander. Their models put Earth at the center. To explain the planet's strange, looping motions, they invented epicycles. Complex circles upon circles, the math worked, it predicted positions, but it was a beautiful, intricate fiction built on a flawed foundation. When Copernicus changed the center, those epicycles melted away. The motion was simple. Our point of view was what had been complex, so some philosophers and cosmologists ask a haunting question. Is our lambda CDM model, with its dark energy and dark matter, a modern epicycle? Are we adding layer upon layer of unseen components to explain observations when the truth might need a simpler, more profound shift in perspective? The issue might be in our definitions, how we define energy in an eternally expanding universe, what the true vacuum of a dynamic spacetime really is. Whether our concept of time itself is complete when applied to the whole cosmos. Our equations are built on concepts forged in labs on planetary scales. Then we stretch them to the edge of everything. That stretch might have created a phantom. Imagine a traveler in a vast desert, seeing a shimmering lake on the horizon. A mirage. He's thirsty, desperate to explain the water, so he invents a new theory. A special kind of water, he says, that exists only at great distances, that can't be touched, but whose properties perfectly explain the glimmer. He writes complex equations about its refractive index, its evaporation rate. All his colleagues agree the math is elegant, but the water isn't there. The illusion was caused by the interaction of light and hot air, by the geometry of the desert and the observer's place within it. The solution wasn't a new type of water. It was a new understanding of perception and environment. Could dark energy be our cosmic mirage, a trick of the geometry between our local position in the cosmic web and the vast, evolving horizon of the observable universe? Maybe our averaging procedures, our assumptions of uniformity, our very separation of the universe into distinct components of matter and space-time, maybe those are the flawed foundations. This proposal offers no easy answer. It offers a challenge to think paradigmatically, to have the courage to consider that the last 70 years of cosmology, for all their triumphs, might be built on an incomplete picture. That the accelerating universe isn't telling us what fills space, but how we misunderstand space itself. It's a humbling thought, an exhilarating one. It means the greatest discovery of 21st century cosmology might not be dark energy. It might be the glaring signal that we're on the verge of a revolution as profound as Copernicus or Einstein. A revolution waiting in the questions we haven't yet learned to ask. So we end this list not with an answer, but with a reflection. In our quest to solve the mystery, have we been asking the wrong question all along? This journey through 30 proposed solutions reveals something deeper than any single theory. It reveals a cosmos alive with possibility, and a human mind courageous enough to question everything, even its own foundations, in the pursuit of truth. We've covered a lot of ground, from Einstein's cosmological constant to brane worlds, quantum loops, the multiverse, 30 different approaches, all trying to explain dark energy. Whether it's changing gravity, adding a new field, rethinking cosmology itself, each one is a serious attempt. It's that basic human need to understand the universe. To take the data supernova light, the cosmic microwave background, and build a story from it. The point of all this might not be which idea is right. The point is the effort itself. Pushing what we know, rewriting the textbooks, looking at the unknown and trying to say something about it. That's how science works. It's not a straight line. It's messy, it's exploring possibilities, and now we're at this edge. The future is more data. New telescopes like Vera Rubin and Nancy Grace Roman. They'll map everything in finer detail. Measure the expansion so precisely that whole categories of theory could fall away. Underground labs, particle colliders, they'll hunt for new particles, new fields. Gravitational wave observatories listening for echoes of cosmic strings, or maybe the hum of extra dimensions. These experiments will test what we've talked about. The evidence will come, and maybe, eventually, these paths start to merge, leading to a new standard model for the universe, one that explains the dark side. So remember, the biggest mysteries aren't dead ends. They're an invitation to wonder, to question, to imagine. They ask for our curiosity and our creativity. If this tour of ideas sparked something for you, let us know. Which of the 30 speaks to you? Leave a comment. For more on space and its puzzles, subscribe. And keep looking up. The next answer, the next discovery might be closer than we think.